Okay. Okay, good evening. Today we are going to learn about the acid-base systems, electrochemistry, and some cells. Actually, electrochemistry belongs to different types of cells. That means electrochemistry and acid-base systems we will be learning today. And here you can see some different types of reactions. And also in one of previous classes, we have mentioned about the buffer solution. So we'll discuss once more about the buffer solution and also the acid base system. Also I have discussed about the acid base, different types of theory, how we can define acid or base, or different types of examples we have given. Again we are going to repeat a little bit more. So acid base Arrhenius theory. So what is the acid, how we can define as the according to the Arrhenius concept. Before discussing this, we are going to discuss about the Bronsted Lowry theory, because we have learned two different theory, Bronsted Lowry and then Arrhenius. So what's the difference between these two ideas? So that is very simple. That means if we go for the Bronsted Lowry system, whatever we have shown in the next slide. So when an acid is a proton donor, actually proton donor, that means if we consider for any acid, that means hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, whatever. So if we consider that something like as acid, then this acid can donate one proton. Actually, what is proton? In last class, we have learned something about the proton and also different types of helium. Not helium. Actually, we have learned the alpha particle. Can you remember alpha particle? Alpha particle was only the two protons, two neutrons. No electrons. It has no electrons, only two neutrons, and it has mass only 2. So in that way an acid is a proton donor. So proton donor, that means H plus. If we consider as a hydrogen atom, so if we can remove one electron from one hydrogen atom, that contains only what it has. If we can have only one neutron, one proton, no neutron. Actually in hydrogen atom it has no neutron. But if we consider some other isotopes of hydrogen, like as what are we have for the hydrogen isotopes, can you remember anyone? What are other isotopes of hydrogen?
Deuterium and tritium.
Exactly, deuterium, tritium, and deuterium has one neutron and tritium has two neutrons, but all the hydrogen isotopes has only one proton. But as we are considering this H plus, that means this is the hydrogen atom leaving one electron. That means when one hydrogen atom releases one electron, then it becomes as proton. So when we consider an acid, all the acid contains hydrogen, and that hydrogen can be donated to someone who can accept the proton. Actually, when we define acid by considering or by using the idea Bronsted Lowry theory, in that case we define that a substance which can donate one proton to someone. In other way or reverse way, we can consider a base is a proton acceptor. That means acid can donate a proton and a base can accept a proton. So here you can see, if we consider NH3, NH3 is a base and water can be considered as acid, and then this water we can write down like this way. So H and then OH we can write down like this way. So H and OH by this way, if we consider like this, so this hydrogen can be donated actually as proton. This proton can be donated to this NH3. So in that case it will be NH4 plus, and the rest of this part OH will remain like this way. So we can consider this NH3 is a proton acceptor, so it becomes NH4 plus, and the water H2O, or we can consider HOH like this way. So this water can donate one proton to this NH3, so it becomes as OH. So here we can consider this water is donating one proton, so water is an acid, and ammonia or NH3, it is accepting one proton, so it is forming as NH4, and it is defined as base or alkali. Similarly, if we consider this NH4 plus, it can donate one NH4 plus, it can donate one proton, so it can, now if we go for this one, this NH4 plus, it can donate one proton to this OH. So this NH4 become acid, and as this OH minus, it can accept one proton, so it becomes as base. So ultimately we are getting the ammonia and water. So here what we are having, if we sum up both the reaction, in that case we can see the NH3 base 1, water acid 2, and this is another acid, and then this is another base. So from here we can see, if we write down or if we consider, this is a base and this is an acid and this is another acid, which has been formed by the accepting one proton by the base. So when this base accepts one proton, it becomes an acid. So this is base and acid. Similarly, this is an acid which converts into a base by donating one proton. So here you can consider this is base and acid. You can consider this is base and acid, a pair. Another, this water and this, this acid and this base, this is another pair. So when this ammonia or this base donates, this base accepts one proton, it becomes an acid. This is a base and acid pair, or we can consider acid base pair. Similarly, when this water or this acid donates one proton to form a base, then we can consider as a acid base pair. Now we will go for the idea what has been mentioned by Arrhenius. So aqueous solution of strong electrolytes. Okay, first we need to know something. Here we have mentioned two terms, weak and strong electrolyte. Actually, the strong and weak electrolytes, it depends on, or we can define the electrolyte strong or weak by the ability to dissociate how fast, or how much. If the electrolyte, if the substance, when it is dissolved into water or when it is in molten state, if it can dissociate completely or it can dissociate a lot. Can you get some noise? Do you get some noise? Hello?
I think it's from Masuma, sir.
No. Some noise can be received from my fan, because I kept my fan a little bit close and it is making little bit, it's making heavy sound, but I do not know. It is clear?
No, sir, it's okay.
Okay, thank you. So just I was wondering if it is making sound or not. So, okay. So a strong electrolyte and weak electrolyte, I have mentioned that if the substance, when it is dissociated or dissolved, or if it is in molten state, if all the ions are separated, or all the ions can be just all the substance can be ionized, then it is considered as a strong electrolyte. And if partly or partially, if the substance dissociate or ionize partially, then it is considered as weak electrolyte. So aqueous solution of a strong electrolyte only exists in ions. That means when we dissolve some strong electrolyte, then in water, aqueous solution of a strong electrolytes, then all the electrolytes are dissociated or converted into ions. So only aqueous solution of a strong electrolytes only exist in ions. Weak electrolytes exist partly as ions, partly as molecules. That means if we have some acetic acid, which is considered as an weak electrolyte. So when we consider or when we take some acetic acid, that means CH3COOH, that is our acetic acid or ethanoic acid. Then if we take this acetic acid and we want to dissolve into water, then we will get acetic acid molecule and acetate ion and proton. But when we dissolve some strong electrolyte like a sodium hydroxide or hydrochloric acid, in that case we will get, if we dissolve into water, here you can see HCl and water, when it is dissolved into water, hydrochloric acid, this is a strong electrolyte. So when it is dissolving into water, that means when we are giving into aqueous solution, then all the ions, that means H plus and Cl minus, we will have all the ions. If we had previously 100 hydrochloric acid molecules, in that case we will have 100 H plus and 100 Cl minus, exactly equal, or completely it can be dissociated or it can be ionized. But if we consider for some weak electrolyte, in that case, if we consider that is like as acetic acid, what I have mentioned, that in case of acetic acid, if we dissolve into water, if we had 100 molecule of acetic acid, in that case we may get 95 molecules of acetic acid and 5 ions, 5 protons and 5 acetate ions. That means 5% of the acetic acid can be dissociated. Just I'm giving a little bit idea, but that number can be varied. So it is not the exact number what I have mentioned, the 5% can be dissociated or ionized. But what I wanted to mean that weak electrolytes, when it is dissociated into when it is dissolved into water, then partly or exist partly as ions and partly as molecules. That means some of the molecules will remain unchanged or it will not be ionized, and some of the molecules will be dissociated. Shoma, what is your question? What is your question?
Message. Can you check it?
Okay.
No, any question? Can you check your inbox? I give you message.
Do you want to leave? You have written here, is it?
Yeah.
Okay. If you have any emergency issue, you can leave. But I am recording the video, so please have the look over the video, and definitely you will have some question from this lecture also in the semester final.
Yeah, Professor, I know. Yes.
Okay. Okay. So if you have any emergency, then you can leave. Thank you very much. Okay.
Thank you, Professor.
Ionic equation for neutralization reaction. So neutralization reaction, what is this? Previously we have mentioned this one several times. Neutralization, that means when an acid and base, when an acid and the base react together, they form a salt and water. So this reaction, actually that is known as reaction between acid and base to form salt and water, that is known as neutralization. Why we call neutralization? Because when we add acid and base together, so acid has some characteristics, acidic property or acidity, and then base has some basicity, and both are just opposite end of the from the neutral. If we consider, so anything neutral should have the value of pH as 7.0. Now, if we consider for the acidic solution, in that case, the value of pH is close to 0 or minus 1, 2, 3, 4, 5, or that means less than 7. And for a base, the pH value is over 7, that means 7 to 14. Normally, we have the value of pH up to 7 to 14 for the base, and for acid 0 to 7. So when we have an acid and a base reacting together to form a salt and water, that types of reaction is considered as neutralization reaction. And if we add one base and one acid, and then it is in aqueous solution. So in aqueous solution, the base is look like in sodium plus ion and OH minus ion. We're considering here both of them, sodium hydroxide, and in hydrochloric acid, H plus and Cl minus. So H plus and Cl minus. So sodium plus, again we are forming sodium plus chloride minus, and then this H plus and OH minus. These two ion, H plus and OH minus, these two ions are forming water molecule, water in liquid state. So ultimately, if we consider the balancing of the left hand side and right hand side, in both sides we have the sodium ion aqueous, and then chloride ion aqueous. So what we have here, you can see that H plus and OH minus ion. So H plus and OH minus ion, we are forming water liquid. So ultimately, the net ionic equation for the neutralization reaction is formation of one water molecule from one hydrogen ion or one proton and one OH minus ion. So actually the reaction between H plus and OH minus to form liquid water, that is the result of any neutralization reaction. So in other way, we can define the neutralization reaction, that formation of one molecule of water by the reaction of acid and alkali or base. So how the reaction is producing 1 mole of water by the reaction of acid and base, that is known as the neutralization reaction. So a neutralization reaction involves a combination of hydrogen ions and hydroxide ions to form water. What we have already mentioned, this hydrogen ion and OH minus ion is forming water in the neutralization reaction. And here we have seen that the common sodium ion, common chloride ion, that can be cancelled out, and for any strong acid and a strong base, we will have exactly similar type of reaction for the neutralization reaction. We may consider sodium hydroxide here, and then sulfuric acid, again sodium hydroxide and nitric acid. In that case, we may, if we consider sulfuric acid, in that case we will have 2H plus, because sulfuric acid contains like this H2SO4. So H2SO4, when we take the sulfuric acid and dissolve into water, then this H2 will be given as 2H plus. So here we will have 2H plus, and then when we will react with the OH, then we need 2 OH minus. So we will have 2 molecules of water. In that case, we will have 2H plus and 2 OH minus to form 2H2 water. So two water molecules will be formed here. So here you can see that only 1 molecule of water has been formed, but if we consider for the sulfuric acid, in that case we will have 2 water molecules. So that is also neutralization reaction. But if we calculate the acidity of this acid, in that case the acidity of sulfuric acid would be twice as that of hydrochloric acid, because when 1 mole of hydrochloric acid reacts with sodium hydroxide, it forms 1 molecule of water, but when 1 molecule of sulfuric acid reacts with sodium hydroxide, it can form 2 molecules of water. So the acidity of sulfuric acid can be considered as double as the acidity of hydrochloric acid. For ammonia, there is no OH. Yes, we have seen for NH3, we have no OH minus. In that case, aqueous solution concept solves the problem. So if we consider we have no NH3, NH3 has no OH. In that case, how we can consider it can give the OH minus, or it can accept H plus. In that case, if we put into water or if we dissolve into water, in that case we can have NH4 plus. So when we dissolve ammonia gas into water, then we can have the ammonium hydroxide. Actually, this is also a base, and when it dissolved into water, it is also forming another base. So actually, it is very difficult to understand that ammonia as a base. But if we consider, if we can dissolve this ammonia into water, then easily we can find out MnS4 OH, which can be easily understood, which can be compared with any other hydroxide containing bases like sodium hydroxide, magnesium hydroxide, potassium hydroxide, or any other thing. So this ammonium hydroxide can be considered as base, and when it is ionized, we are getting NH4 plus and OH minus. So we can easily understand that now NH4 plus, it is can be considered as acid, and this can be considered as base. So here we have seen how we can have the idea about acid and bases, and how we can dissolve into water to give the H plus or OH minus. Okay, now already I have mentioned about the conjugate acid and conjugate base. Conjugate acid, already mentioned about that. Let's see this. When hydrochloric acid donates one proton, it becomes as Cl minus. That means the acid 1 and this is our base 1. So this acid 1 and base 1, they are called as conjugate acid base pair. That means when either acid or the base, by donating or accepting a proton, they can transfer from acid to base or base to acid. That pair is considered as conjugate acid base pair. So for any neutralization reaction, we will have the idea, at least we will have two conjugate acid base pairs. Here you can see that acid HCl and Cl minus. This Cl minus is formed by donating one proton. So this is our acid and this is our base. So this base can accept one proton to form the acid. That means in that case, this base is working like as base, and it can accept one proton to form the acid. Again, this water is accepting one proton from this. So here this water is working like as a base, and after accepting, what is the question? What happened? Sir, I have sent the paper. Yeah, I will check it, but not now. So when this acid, when acid is donating one proton, it is forming a base. Again, when this base is accepting one proton, it's forming as a acid. Therefore, we are having two pairs, acid base pair. This is another acid base pair. So in any neutralization reaction, we are having two acid base pair. And if we consider to define the conjugate acid or base pair, then if the acid or base, by donating or accepting one proton, it can convert into another acid or base, then we will consider that pair. That means when this acid donates one proton, it forms a base. So this acid and base, these are one conjugate acid base pair, and similarly this base and this acid, they are considered as one conjugate acid base pair. So here we have some example. This is ethanoic acid, what I have mentioned. So ethanoic acid is reacting with water to form the, this is ethanoate and this oxonium ion. So here you can see that this base and this is acid. So this acid, when it is donating one proton, then it forms this base, and this base is accepting one proton to form the acid. So these are conjugate base acid base pair, these are conjugate acid base pair. So if you have any reaction, then you have to understand which one is formed. So this is one conjugate acid base pair, this is another conjugate acid base pair. Okay, self ionization water, that is very interesting. That means till now we have seen one substance can be considering as like as acid or base. That means sodium hydroxide, this can be considered as a base. Hydrochloric acid, that can be considered as a acid. But water itself, sometimes it can be considered as neutral, sometimes it can be considered as acid or can be considered as base. Actually, the power or the acidity or basicity is compared with something. If we have two different chemicals, then we can compare among these two who can donate one proton faster. So those, if we consider for previous one, this hydrochloric acid, this HCl can donate one proton faster than water. Therefore, this can be considered as acid and this can be considered as base. But if we have some example where this water, here we are showing that water is base, and if we consider some example, that means if we want to react with something or someone or some compound which has the less possibility or less probability to to donate a proton, in that case this water will have more ability or the faster ability to donate a proton. In that case, we can consider that water as an acid. So here you can see, here we can see that two water molecule are reacting together, and one water molecule can donate one proton to, that means this water molecule is donating one proton to this. Therefore, this water molecule behaving like an acid and this water molecule behaving like as base. Therefore, we can see that from this water it is forming oxonium ion, hydronium ion, and for this water it is forming OH ion. So from here, this is water, this is acid. This acid, it is forming a base. So here you can see that this is conjugate acid base pair and this is conjugate acid base pair. And here we can see from two water molecule, ultimately we are having, that means when one water molecule is dissociating, we are having H plus ion and OH minus ion. So the water molecule itself can behave sometime like as an acid or sometime as an base. Therefore, the self ionization, that means water can give proton to some other water molecule, and that means ultimately one water can behave like as acid and another water can behave like as base. Therefore, we can consider that water is a self ionized compound. So water and water, both of them giving both of them are participating. So we are having OH minus and H3O plus. So here again we can see for water molecule or liquid water, when we dissolve into water, that means liquid water, it is forming H plus and OH minus. So we have learned the chemical equilibrium, and also we have learned the equilibrium constant. So if we can write down the equilibrium constant for this reaction, in that case the equilibrium constant will be the multiplication of the concentration of the products. Here you can see we have two products, H plus and OH minus, and we have one reactant. So the equilibrium constant K equilibrium would be multiplication of the concentration of the products. Here two products, H plus and OH minus. So here we are writing the multiplication of two H plus and OH minus and the concentration of the reactants. Here this is the concentration of the reactants. So we are writing the chemical equilibrium or equilibrium constant by this formula, and in naturally or generally the concentration of water, liquid water, is very high, 55.55 mole the concentration. So if we consider this is very high concentration and this is a constant value, so we are having, this is a constant term, that means K equilibrium multiplied by concentration of liquid water equal concentration of H plus multiplied by concentration of OH minus. So we can express this K equilibrium multiplied by this concentration of water, liquid water, as KW. KW, that means the equilibrium constant or dissociation constant of water. That means this is water molecule. So this is the dissociation constant of water, and that can be represented by as H plus multiplied by concentration of H plus multiplied by concentration of OH minus. And experimentally, we have found the value for the KW. Experimentally, scientists have found that the value of KW, that means the dissociation constant of water, is 1.0 into 10 to the power minus 14. So we can write down the KW equal 1.0 into 10 to the power minus 14 equal concentration of H plus into concentration of OH minus. So the value of KW equal 1.0 into 10 to the power minus 14 equal, here we can write down, that is equal, these are equal. So H plus multiplied by OH minus equal 1.0 into 10 to the power minus 14. Now we will use this value to calculate the value of pH for some compound or water, pH and P of OH. So previously we have seen that the value of water dissociation constant, as here you can see 1.0 into 10 to the power minus 14. Before going there, we want to define the pH or P of OH. Any of you have idea what is the value definition of pH and P of OH? Anyone? pH, here you can see the definition. Yes, pH, or we can write down the K, not really. This is the pH. Actually, the concentration of H plus, you can see the negative logarithm of concentration of H plus. If we have a solution, that means either acid solution, base solution, or any compound, if we have the value of concentration of H plus, and then if we take a negative log of H plus, or that means the concentration of H plus, this is the value of pH. pH is defined as the negative logarithm of H plus. Therefore, we can have the value of pH, pH equal minus log of H plus, and similarly, we can define the value of OH or P of OH, that is P of OH equal minus log of OH minus. So for any solution, if we have the pH and P of OH, P of H or pH is defined as the pH is defined as the negative log of H plus, and P of OH is defined as the minus log of OH minus. This is the concentration of OH. How much concentration, or in any solution, what is the concentration of OH per minus? And if we take the negative logarithm of my OH minus concentration, then that is the value of P of OH. So here, now in case of water, as we have seen in previous slide, I'm going to back. So here we have seen that the KW equal 1.0 into 10 to the power minus 14, and we have seen this is the water dissociation constant, and the water dissociation constant equal H plus, concentration of H plus multiplied by concentration of OH minus. So we can write down this term equal to this, and then we can go for here liquid water H plus and OH minus, KW already we have seen in previous slide. So H plus, now H plus equals and equal 10 to the power minus 7. The concentration of H plus, the concentration of H plus and concentration of OH minus, that is both of them. When one water molecule is ionized, then we are getting one H plus and one OH minus. So undoubtedly we can consider that when the concentration of H plus, if we can determine the concentration of H plus in the solution, then we can easily find out the concentration of OH minus. Here you can see the concentration of H plus is 10 to the power minus 7 mole, and the concentration of OH minus also 10 to the power minus 7 mole. So if we write down this minus log Kw, previously we have found the Kw equal 1.0 into 10 to the power minus 14. So this is the equation. So if we take minus log for both side of the equation, minus log and then minus log. So minus log Kw equal minus log H plus aqueous multiplied by OH minus aqueous, and then as we have minus log, or let us consider we just consider only we have the log for both of them. So as we have the log, then if we distribute the log term to this, so we will have log H plus plus log OH minus. So as we had one minus sign, so we are giving the minus sign for both one, minus log H plus minus log OH minus. So this is the definition of pH, and this is the definition of P of OH. So here you can see the minus, already have mentioned the value of Kw is equal 1.0 into 10 to the power minus 14. 10 to the power minus 14, we have mentioned that. So if we write down the minus log of 10 to the power minus 14, that becomes 14. You can use your calculator to find out the value. Minus log over 10, log of 10 to the power minus 14, you will have the value of 14, and this is the definition of P of OH, and this is the definition of P of OH. So we are having the value of pH plus P of OH equal 14. So for any water system, for any water, the value of pH plus P of OH equal 14. That means the value, actually this is the pH, value of pH is 7 and 7. So ultimately we are having the value of, because we have mentioned the concentration of H plus, the concentration of H plus in water, that means the concentration of this and this is equal to minus 10 to the power minus 17, or 1.0 into 10 to the power minus 7. So 1.0 into 10 to the power minus 7. So minus log of 10 to the power minus 7 become plus 7, and minus log of 10 to the power minus 7 become plus 7. So 14 equals 7 plus 7 we are having. So you have no question yet. Now we have to calculate one value of pH and P of OH. A strong acid and a strong base, already we have mentioned about that. The substance or electrolyte we have mentioned about in terms of electrolyte, but in case of acid and base, if we want to define the acid and base as a strong acid and a strong base, in that case we can have the idea. That means similarly what we have mentioned for the electrolyte, that means the strong acid and a strong base, that can be defined as if the acid can be ionized, or if the acid can dissociate to form the ion, or all the proton can be donated, or all the acid can be ionized, that means completely ionized, that is known as for strong acid. Or if we consider for base, if the base can be completely ionized, that is a strong base, and opposite is weak. That means if the acid or base cannot be completely ionized, or it can be ionized partially, that can be considered as weak base. So now here we can see we have some example. Calculate the concentration of H plus and concentration of Cl minus and concentration of OH minus in 0.015 mole of HCl. So you have a solution, hydrochloric acid solution. So when we consider that the hydrochloric acid, this is a strong acid. So a strong acid can be completely ionized. So if you have the strong acid 0.015 mole of hydrochloric acid, now how much what would be the concentration do you expect for the H plus? We have the acid HCl. HCl we have mentioned that is a strong acid. So if it is a strong acid, then how many ions of hydrogen and how many ions of chloride we are expecting for this? Anyone have idea? What is the value of H plus should be? Concentration of H plus. Nobody is here.
0.015.
Yes, that is your answer. Now I would like to know what is the reason.
Because that is the concentration of HCl, and as it is a strong acid, the concentration of hydrogen should be the same.
Exactly, because as we are looking here, the hydrochloric acid is a strong acid, and when we dissociate this strong acid, that means the acid will completely ionized. So if we had 5 moles or 5 molecules of hydrochloric acid, it will form 5 molecules of hydrogen ion and 5 chloride ions. Just exactly how many molecules of hydrochloric acid we had, or how many moles of hydrochloric acid we had, we will get exactly same number of moles of hydrogen ion and chloride ion. So now we can see that the concentration of H plus is 0.015 mole. Now we can find out the value of pH. If it is possible, we can find out the value of pH. Value of pH we have mentioned. Value of pH equal minus log of concentration of H plus. Already we have mentioned the value of H plus 0.015. So that is the value of concentration of H plus. So just if you use your calculator, minus log of 0.015, then you will get the value of pH. Anyone can use the calculator, please. Just calculate minus log of 0.015. What is the value of pH? Minus
1.82.
1.82 or
Yes.
83. 82.
82390. So 82.
Okay, thank you. So now we are having the value of pH, but now you have to find out the value of P of OH. But here we have nothing mentioned about the P of concentration of H plus. Sorry, OH minus. Do we have anything?
No, but we have to minus it. Like
Yes,
7 minus
as we
pH.
have shown in the previous slide. Oh sorry, I could because so in the previous slide we have seen P of H plus P of OH minus, or P of H plus P of OH equal 14. So right now we have find out the value of P of H equal 1.823. So if you want to find out the value of P of OH, just you can subtract from 14. So in that case, P of OH that should be equal 14 minus 1.823. That is very simple. So by that way, you can find out the value of pH and P of OH. Okay, 12.177. Thank you. Okay, so we are moving forward. Lewis acid and base. Okay, now everywhere we have mentioned about acid and base. Up to this we have mentioned about either proton or considering the water solution in water. So we have two different idea, but if we have some other compounds where we do not need to consider, if we have to consider always the water, in that case some other compounds we cannot consider as acid or base, but it has some characteristic that some other compounds also can donate some pair of electron or accept some pair of electron. So by the ability of donating or accepting the electron pair, we are defining some compounds as acid or base. So Lewis acid. So Lewis acid, here you have no proton. That means this one, if we consider for this one, we have no proton here. BF3, boron trifluoride. So in this compound, we have no proton, so it cannot donate any proton. So we cannot consider as acid, but it is acid because if we have the value of pH or P of OH or the dissociation constant of BF3, in that case the value is quite high, and also we can consider this is an acid. And then how we can define the Lewis acid or this types of acid where we do not have any proton? So electron pair acceptor, if we consider this is ammonia, so this ammonia has one lone pair. That means nitrogen is bonded with 3 hydrogen atoms by 3 covalent bonds. Here we can see one covalent bond, this is another covalent, this is another covalent. So 3 hydrogen atoms are bonded with 3 hydrogen atoms, and this nitrogen atom has one extra pair of electrons, and that pair of electron can be donated to someone else who have the deficiency or who has the ability to gain one pair of electron. So when this one pair of electron is donated to this proton, this boron, that means actually this boron has, previously we have mentioned in another slide, another lecture, that means boron trifluoride, this do not follow the octet rule. We have mentioned the octet rule, that means every atom has the tendency to make the outermost shell having 8 electrons. But if you count for this compound or boron trifluoride, this fluorine has 8, fluorine has 8, fluorine has 8, but this boron do not have 8 electrons. It has only 6 electrons. So if it can gain one pair of electron from someone else, then it can fulfill the octet rule and it can become more stable. So this boron is accepting this lone pair of electron from ammonia. Therefore, this ammonia is donating one pair of electron. So we are defining this ammonia as a Lewis base because it is donating one pair of electron, and this boron trifluoride, it is accepting one pair of electron. So we are defining this boron trifluoride as an Lewis acid. So just define oppositely. Previously we have mentioned for acid and bases, if a proton can be donated, that is an acid. Now if electron can be accepted, if a pair of electron can be accepted, then it is called as acid, Lewis acid. So after gaining the one pair of electron, it is making a coordinate covalent bond between this nitrogen and boron. So it is making the compound a more stable compound. So by this formation or by this reaction, this is a base and this is an acid. So this is also a kind of neutralization reaction. So acid and base reacting to form a, ultimately this is a conjugate or complex compound, but sometimes it can be considered as salt also. But just let us consider this is an base, this is an acid. So we are having the neutralization reaction, this acid neutralizing this base. Therefore we are defining the acid and base like this way: electron pair acceptor, who can accept a pair of electron, that is known as acid, Lewis acid, and who can donate a pair of electron, that is Lewis base. Okay, so dissociation of weak acid, weak electrolytes, or weak acids and weak bases. Already we have mentioned about that, weak acid or weak base or weak electrolyte. Weak electrolytes are ionized to only a slight extent. Just if we consider, that means weak electrolytes cannot be completely ionized. just a strong electrolyte ionized completely. So a weak monoprotic acid, if we consider now, this is one new term, monoprotic acid. What does it mean? Monoprotic acid. Anyone have the idea what is the meaning of monoprotic acid?
Having one proton?
Yes, having one proton or the ability to donate one proton. Yes. So if substance or if the acid can donate only one proton, or if it has only one proton to donate it, that is monoprotic acid, and that is hydrochloric acid, nitric acid, that can be considered as monoprotic acid, and diprotic acid, that means sulfuric acid, and triprotic acid, it can be phosphoric acid, H3PO4, like this. So that are monoprotic, diprotic, and triprotic acids what we are defining. So the extent to which the weak electrolyte dissociates is expressed by either ionization constant or degree of ionization. For anything, how much or how percentage, what is the percentage or what is the amount of the acid, weak acid, as already you have mentioned, for the strong acid and a strong base, it is dissociating completely. So in case of weak acid or weak base, it do not dissociate or it do not ionize completely. So what is the fraction, what is the percentage, or what is the portion of the weak acid or base is dissociating or it is ionizing, that can be expressed by the using these types of formula. We can use the Kc dissociation constant. Dissociation constant, that means how much. Here we can see, let us consider a weak monoprotic acid, Ha plus water. This is an acid and then this is a base. So when this acid is donating one proton to this base, it is forming these types of compounds. So this is our conjugate base, and this is base, and this is conjugate acid. So ultimately, as we have learned about the dissociation constant or equilibrium constant, so we can write down the equilibrium constant for the ionization. When the monoprotic acid is ionizing, then we are having the ionization constant or equilibrium constant by this formula. As already have mentioned, the dissociation constant by or equilibrium constant would be equal to the multiplication of the concentration of the products divided by the multiplication of the concentration of the reactants. So these are two products. So here we are writing the concentration or multiplication of the concentration of the products divided by the multiplication of the concentration of the reactants, Ha plus H2O, H2O multiplied by Ha. So the concentration of this water and Ha. So here we are having, now as we have mentioned that this water, the water dissociation constant already we have learned. So the concentration, when we know the concentration of water is very high, so just we can consider or we can use this water, we can write down this water, concentration of water along with this Kc. So that can be considered as constant. So we can write down Kc multiplied by the concentration of H2O. Concentration of H2O, here you can see Kc multiplied by concentration of H2O equal H plus multiplied by A minus. That means we are representing this as H plus. Actually, we don't need to write down this as H3O plus. So we are writing just H plus and then A minus and then divided by the Ha. So the dissociation constant, acid and base ionization constant, these are the acid ionization constant and this is the base ionization constant. So for any acid, if you have any weak acid and weak base, so if you have any, now you can have the idea what would be the value of the acid dissociation constant or the base dissociation constant for any weak acid and weak base. If we have the value of this one, we have mentioned that the dissociation or ionization of the weak acid is very less or partially ionized. That means the concentration of H plus and concentration of A minus, that would be very less. That means that value would be very small value. And this one, that is the concentration of our pure acid. That means undissociated acid, or the molecule, acid molecule, which is not dissociated or which is not ionized. That means the concentration of this undissociated acid is very high. Therefore, the concentration of these and these are very low or very small value, and this has a very large value. Therefore, ultimately we are having this ratio a very small number. So we can have the idea about the acid dissociation constant, that should be a very small number, because when we divide a very small number with a very large number, we are getting again very small number. So the acid dissociation constant for a weak acid or the base dissociation constant for a weak base is a very small number. So you can easily understand for any, that means for any strong acid and a strong base, you can easily understand that means we will have nothing here. If we consider for hydrochloric acid, in that case, we will have all the hydrochloric acid molecules will be converted into H plus and Cl minus. That means the concentration of H plus and Cl minus would be very high, and that would be close to 0. That means the concentration of HCl would be close to 0. That means we will have a very large value for the products. That means the concentration of H plus and concentration of Cl minus, that is a very large value and that is a very small value. So when we divide a very large value with a very small value, then the ratio or the total value becomes even larger. Therefore, we can have the idea, that means for a strong acid, the dissociation constant, acid dissociation constant or base dissociation constant for a strong acid or a strong base is very large number, and for weak acid and weak base, the acid dissociation constant or the base dissociation constant is very small number. Okay, now the buffer solution. Already we have learned about this. So buffer solution. If we have a solution of a weak acid, let us consider this is a weak acid, acetic acid, and we are dissolving this weak acid and the base, then conjugate acid and conjugate base are formed. From this one we are having the conjugate base, and for this one we are having the conjugate acid. So here we can see the dissociation constant for this one, acetic acid. If we find out the dissociation constant for this one, then we are having this. So that is 1.8 into 10 to the power minus 5. That means the acid dissociation constant for acetic acid is very small number, 1.8 into 10 to the power minus 5. Still, this is quite a large number. Even we have very small number. Sometimes we may have the acid dissociation constant value 1.8 into 10 to the power minus 18. That means that is very small. So the dissociation constant, even in case of water, we have found that the dissociation constant is 1.0 into 10 to the power minus 14. That means the water itself, it is not a very strong acid nor a strong base. That means the dissociation constant for acid as water is 1.0 into 10 to the power minus 14, or as a base, that is also 1.0 into 10 to the power minus 14. That means the water as acid or base, the dissociation constant is very small. And here we can see the weak acid and its conjugate base. When we are having a solution of a weak acid and its conjugate base, then if we add a small amount of acid, that means as H plus, or a small amount of base as OH minus, then the value of pH changes very little or negligibly. That means if we have a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid, then if we add a very small amount of acid or a small amount of base as H plus and or OH minus, in that case the value of pH for that solution changes very little or negligibly, then we can consider or we can define that solution as a buffer solution. And these types of buffer solution are used in different purposes. So for some reaction, if we need to adjust or if we need to control the value of pH for a quite long range, in that case we need to use the buffer solution. So that if we add a small amount of acid or as H plus, here you can see this is a buffer solution. That means we have mentioned weak acid and its conjugate base, or weak base and its conjugate. This is a weak base and its conjugate acid. So that is a buffer solution. So when we add a small amount of H plus, here you can see addition of H plus. If we add a small amount of H plus to these types of buffer solution, what happens? Addition of H plus, then we had a lot of or some number of acetate ions. These acetate ions will combine the additional H plus. That means what H plus we are adding to the buffer solution, that will add to the acetate ion to form a acetic acid, and the value of pH of acetic acid will not change huge. That means the value of weak acetic acid, the acetic acid is very negligible. That means what already we had in the solution, in the buffer solution, we already had the acetic acid. Therefore, it will increase the amount of acetic acid little bit, but the value of pH or the concentration of acetic acid will not increase huge. Therefore, the value of pH will not change too much. Again, if we add a small amount of OH minus, in that case, if we add a small amount of OH minus, that means any hydroxide in the buffer solution, what will happen? That OH, that means that OH will combine with the H plus. That means when we are having this acetic acid and this is weak base, so we are having, then we will have some proton already we have. So this proton combining with this OH minus to form water, and in the solution we already had the water, and the value of pH for water is 7, and it is not changing at all. Therefore, when we add a small amount of OH or a small amount of H plus to the buffer solution, the value of pH do not change significantly, or it is changing very little. That means when we add little bit more, in that case the value of pH can be changed a little. However, normally if we add a small amount of H plus or OH minus, or that means a small amount of acid or a small amount of base, in that case the value of pH do not change for the buffer solution. So the pH value change only very slightly in addition to a small amount of acid or base. Just if we add a small amount of acid or base, the value of pH changes very little. A weak acid and its conjugate base, already mentioned, that means a weak acid and its conjugate base, or a weak base and its conjugate acid. Here you can see this is weak base and its conjugate acid. So weak base and its conjugate acid, or weak acid and its conjugate base, that is known as the buffer solution. Okay. We are not going to learn this one, just skipping this, and then calculating the pH of a buffer. Now, how we can calculate the pH of a buffer solution? Already we have signed that the Ka, or the acid dissociation constant for a buffer solution, for that means the buffer solution we have prepared with acetic acid and the acetate ion. That means the weak acid and its conjugate base. So we can have the value of Ka, or the acid dissociation constant for the weak acid, equal like this way: Ka equal acetate ion multiplied by the concentration of hydronium ion divided by the concentration of acetic acid. So that is the value of 1.8 into 10 to the power minus 5. So now 25 gram of sodium acetate dissolved in 0.55 mole acetic acid to make 500 milliliter buffer. So we are dissolving this 25.5 gram of sodium acetate. Sodium acetate dissolved in 0.55 mole of acetic acid. That means the concentration of acetic acid already we know. So the concentration of acetic acid is given here, and you know the acetate. Actually, here is given the acetate, sodium acetate. Sodium acetate, if you have, this is the mass of sodium acetate. So you can have the value of number of moles on the concentration. You can find out the number of moles of acetate because we know the mass of sodium acetate. Now you can divide with the value of sodium mass of the molecular mass or molar mass of sodium acetate with this number. So 25 divided by the molecular mass of sodium acetate, then you will get the number of moles of sodium acetate. So then you have to dissolve into 500 milliliter. That means the volume becomes 500 milliliter. So if the volume is 500 milliliter, so you can have the value of concentration of this. So you can have the, here you can see, calculate the molarity of salt. You can see this is the molecular weight, 82.04. So this is 25 grams. So number of moles, if we want to find out, the number of moles equal 25.5 divided by 82.04. Then the volume, this is 0.5. Here we have mentioned 500 milliliter. So in liter, it should be 0.5 liter. So the concentration, that means the molarity of the sodium acetate, should be 25.5 divided by 82.4 divided by volume. We know the concentration formula equal like this way: number of moles divided by volume in liter. So number of moles equal, again we can write down a small m divided by capital M. A small m is the mass of the substance and capital M is the molecular weight. So here you can have the volume in liter. So 25.5 divided by 82.04 divided by 500 milliliter, we are converting into 0.5 liter. So equilibrium constant we are having, this is the value of equilibrium Ka value, and then you can find out what, calculate the pH. So you have to find out the concentration of this. You have to find out the concentration of this. We are having the concentration, everything. So we have the concentration of this, we have the value of Ka, and we have the value of this one, and then we can calculate the value of concentration of this. That means this is the concentration of H plus. So we need to find out the value of pH. Once we can find out the value of concentration of this hydronium ion, then we will use the minus log of H plus, minus log of H plus concentration, or H3O plus. So H3O plus is the H plus. So that would be the value of pH. So another thing, Henderson-Hasselbalch equation for preparation of buffer solution. If you want to prepare a buffer solution of your intent buffer pH, intent pH, what is the value of pH you want to prepare? In that case, if you want to prepare a buffer solution of pH 4, in that case, the value of pH should be 4, and then we have to find out the way, we have to use the pKa log conjugate base and conjugate acid. The concentration, how much? What is the concentration should be the conjugate base, and what is the concentration of acid, conjugate acid? We need to take that. By that way, we can easily find out what would be the value of pH, or if we want to prepare the value solution, buffer solution at a certain pH, then we can use these types of equation to find out what mass of sodium acetate should be dissolved in 0.25 mole of acetic acid to make 300 milliliter buffer buffer with pH of 5.09 Ka. We have the value of pH, we have value of Ka, that means we can find out the value of pKa and the dissolve into 0.25 mole of acetic acid, that means the acetic acid concentration is given here, and then you have to find out the concentration of base, that means what mass of sodium acetate. So first you have to find out the concentration of conjugate base, that means sodium acetate, and then you have to go back to the mass using this formula. First you have to find out the number of moles, and then you can use the mass equal Nm. So number of mass equal N into M. So that is the M equal Nm. That will be the formula. You can easily calculate. Now neutralization curve. That is something what we have mentioned regarding the titration. So neutralization and neutralization curves. So if we want to neutralize a base with an acid, or if we want to neutralize a base with an acid or other way, in that case, what happening or what is going to happen here, and how we can understand when the reaction is over or the neutralization is complete. So in that case, already we have mentioned that one. I think I have shown you these types of graph, and also I have mentioned you how we can do the titration, what types of indicator we can use. So just today we are going to discuss in very simple. That means for the strong base, the value of pH is close to 14. That means for a strong base, the value of pH is very high, and for a strong acid, the value of pH is very. Here you can consider a strong base, a strong acid. If you consider for a strong base, the value of pH is very high. For a strong base, a strong acid, if we start with a very strong base and then we are adding little bit acid, and we are adding a little bit acid, and then the amount of base is neutralized by the acid what we are adding. That means when one OH, let us consider in case of a strong base, we have OH minus, and as acid we are adding the H plus. So if we add one H plus to the one OH minus, then one OH would be neutralized by one H plus. So when we have 500 OH minus and we are adding one by one, or 5, 10, 20, 50 H plus, in that case the amount of the H plus OH minus will be reduced with time with addition of H plus. So at a certain period of time, we will see that there will be no OH minus and no H plus. At that point, the value of pH would be exactly 7. If we put a pH meter into the solution, you can do normally what I have mentioned in the previous class. We can use the pH indicator or that neutralization or acid base indicator. In that case, we can have the idea, but even without having the indicator, you can have or you can do the titration for the neutralization reaction. Just if you have a pH meter, and then first you have the pH meter inserted into base, then you are adding a little drop of acid, and then you are stirring the solution. Then you are getting the value of pH is decreasing, and at a certain point you will see the value of pH is exactly 7. That means that is the end point. That means at that point there will be no OH minus and H plus. Now if you add few more drops or few more excess H plus, in that case the concentration of H plus will increase and the value of pH will be decreased rapidly. So in that case we will have the value of pH changing like this way. So when we titrate for the strong base with a strong acid, then the titration curve looks like this way. And here you can see the value of pH changing little bit, and then here changing little bit, and sharp decrease. And here you can see for a strong base and weak acid, the end point, here is our end point, and the pH of after the completion of the titration, the pH value do not go close to 0. It is quite high. That means the value of weak acid is very large and close to 7. Therefore, for the strong base weak acid, the titration curve looks like this way. And for weak base strong acid, for weak base, the pH of weak base is close to 7 or little bit higher than 7, not close to 14. So when we start the titration with a weak base with a strong acid, in that case we will gradually or rapidly we are decreasing the value of pH, and then at value of pH equals 7, it has a sharp decrease, but not too long, as we have very long or rapid drop. Here you can see a rapid drop, but here no rapid drop, here also not rapid drop, but moderate. You can consider this is a moderate, this is moderate, and this is no decrease. Actually, this is very difficult to distinguish where is the end point. So, and at the end, as we are adding a strong acid, so after the end point, as we are adding a strong acid, in that case, the value of pH is decreasing sharply and it is becoming close to 0. That means we are having the value of pH is close to 0 or very close to 0. That way we can identify the, that means the titration graph for the weak base and a strong acid will be like this. And for a weak base and weak acid, for weak base, the pH value is close to 7 or little bit higher than 7, and for a weak acid, that is also close to 7 or little bit lower than 7. So when we are at the end point, still it is going decreasing little bit like this way. So no sharp change, just at somewhere when you are adding little bit more acid, just we can see if we have the pH meter very sharp, then we can have a value of pH equals 7, but that is very difficult because that is not sharp change, and we can have these types of. Now neutralization titration curve we have learned about. If we have 4 different types of condition: a strong base weak acid, a strong base weak acid, sorry, a strong acid, weak base, a strong acid, weak base, weak acid. So 4 different types of titration curves. You need to have these types of idea, because I may give these types of graph. When you are titrating a strong base with a weak acid or a strong base with a strong acid, what would be the titration curve? What would be the titration curve pattern? So please remember this, so you can have a question from this. Then pH indicator. This is some medium or some substance. When we add into a acid or base solution, depending on the pH of the solution, we will observe a specific color. So just observing the specific color, we can have the idea what is the value of the pH without having the pH meter. pH meter is little bit expensive, so you can use different types of indicator that is not so expensive. So just you can, but that will not give you the exact value, but you can have the idea what should be the range. Here we have different types of pH indicator. That means different types of compounds. We can have the idea what would be the pH of the solution without measuring the exact value, or what is the range of the value of the pH of the solution. We can have either acid or base or neutral water or whatever. So just if you have these types of indicators, and then if you dip into your solution, then you can have the idea about what would be the value of pH for this types of solution using these types of indicator. That means when we are adding a specific indicator to a solution, then we are observing a certain color, and observing the certain color or the what types of indicator we are adding to the solution. Based on that, we can have the idea about the value of the pH or the idea about the solution, if the solution is acidic or basic, or if it is highly acidic or highly basic, or whatever it is. So that are the substances we are using as a pH indicator. So now electrochemical series, that is little bit more important. Electrochemical series, something we have learned something about the in the periodic table. You can see my background. In the periodic table, we have seen many things. That means in the periodic table, we have seen the metals are increasing the reactivity from top to bottom, non-metals increasing the reactivity from bottom to top, and also the reactivity and many other properties we have seen. But we have different types of metals: sodium, potassium, sodium, calcium, magnesium. All the metals, all the metal atoms have the tendency to donate some electron. But overall, in the periodic table, we have organized or arranged all the metals or the atoms according to their electronic configuration. Just all the group 1 element in the group 1. That means the elements having 1 electrons in the outermost shell, we have organized them in the group 1, and rest of them in the group 2, group 3, group 4, like this way. But if we compare all the metals or all the atoms together, then how we can have the tendency, or which one is the most powerful element, or our most powerful metal. That means which element or which metal can donate faster than any other element. That means, as we have mentioned, for the metal, the reactivity is measured, or the reactivity is the ability to donate electron. So when we are having one metal, it can donate 1 electron. So for the potassium, if we have some solution in where we have potassium, sodium, calcium, magnesium, and in that case, the potassium will donate electron faster than any other elements in the group or even in the periodic table. So the tendency, if we organize all the elements or all the metals in a series where the organizing capacity or organizing property is measured by the ability of donating electron, that is known as the reactivity series of the metals. So if we have some solution, or if we have some mixture, in that case, this potassium will have the tendency to donate the electron faster compared to any one in the series. Even if we have calcium and magnesium, or calcium and iron, in that case, the calcium will have the possibility to donate electron faster than magnesium or even any other elements. So if we have anything in this reactivity series, any metal who is in the above position, that can donate electron faster than any other in the lower portion of the series. So you have to remember, maybe I'm not going to give you in the exam for this, but it is very important, those who have some interest to learn what types of reaction or what types of cell we can prepare. So I have memorized all of them: potassium, sodium, calcium, magnesium, aluminum, zinc, iron, then lead. We had another one: cobalt, tin, cobalt, lead, hydrogen, copper, magnesium. But one thing, you better understand or you better remember hydrogen is below the lead. Hydrogen in the below or lead is above than hydrogen, and copper is below the hydrogen. That means if we have two electrodes in any system made of hydrogen and copper, in that case hydrogen can replace the position of copper, but the reverse way it cannot. Or if you have any reaction with reacting with copper, but if you have sodium and hydrogen, then hydrogen cannot replace the sodium, but sodium can replace hydrogen. That means sodium can push out hydrogen from somewhere, but hydrogen cannot push sodium to somewhere else. So that is the actual idea about the reactivity series. That means how fast or how efficiently one element or one atom or one metal can donate electron compared to other. That is the reactivity series. If we organize or if we arrange all the elements according to their capacity to donate electron, that is known as electrochemical series or reactivity series. So this gold, the gold is the least reactive metal. We have mentioned several times that all the ornaments are made of different types of sorry, I didn't see your question earlier. So can only donate one proton? No, sorry, I think you have answered another question. Monoprotic, that means. So I have mentioned about the gold. The gold, that means the least reactive metal. If gold was or give gold would is a reactive metal, in that case nobody could use the gold as ornaments, as gold has very less tendency to donate electron to someone. Therefore the reactivity of gold is least among the available metals in the universe. Okay, so now we are going to learn about the half cell. Half cell, that means before going to have idea about the half cell, all of you have seen different types of cells, like a dry cell, that means the battery, what we call it, dry cell. That means sometimes we have in our mobile phone we have some cell, but that is different types of cell. We have two types of cell. One would be considered primary cell, another would be secondary cell. So if the primary cell is just it can be used only one time, and secondary cell it can be used multiple times. Why it can be used multiple times, we will be learning that way. First you have to learn about the electrochemical cell and electrolytic cell. These are two different terms, electrochemical cell and electrolytic cell. So what is this difference? Electrochemical cell and electrolytic cell. So electrochemical cell, that means if we have some solution, if electricity is generated by the chemical reaction, if electricity is generated by the chemical reaction, that is known as electrochemical cell. And electrolytic cell, if the chemical reaction happens by the passing of electricity. So if we pass electricity through any cell, then if the ions are dissociated or the reaction proceeds, that is known as electrolytic cell. And if we have, that means normally when we use our mobile phone, what happens? In our mobile phone we have some battery, and then during when we are doing something in our mobile phone, we are using the battery. That means in that case we say that we can consider the reaction, chemical reaction inside, because in the battery, inside battery we have some chemicals, and that chemicals are reacting together to generate some electricity. Using that electricity we are using the mobile phones. Now when we are recharging the mobile phone, what happens? We are passing electricity through the battery, and that time the electricity is passing through the chemical, and the chemical reaction is happening other way. What was previously we have mentioned, when we are using the mobile phone, that time the electricity is generated by the chemical reaction. Now if we consider for any cell, we have two different parts. Actually better we go for here. If we consider for any cell, we have two different parts. One as electrolyte dipped in, one electrode is dipped into an electrolyte, another electrode dipped into an electrolyte. So actually two different electrodes and two different or same electrolytes. So this one electrode and one electrolyte, that is called as half cell. Another electrode and another electrolyte, that is called as another half cell. So when these two half cells are connected by a connection, that means when we are using our mobile phone, that time this connection are just, if we turn off our phone, that time this connection is just disconnected. That time no electricity is passing or no electricity is using, therefore nothing we can use or nothing it can be seen in the display. So but when our phone or any other device is on, that time these two half cells are connected together. So this is one half cell, this is another half cell. That time the electricity, that means the chemical reaction between these two half cells proceeds. So what happens that way, when this is one half cell, this is another half cell. So when these two half cells are connected by a solid bridge and with some other circuit, that time some chemical reaction proceeds in between these two cells, and with the chemical reaction the electricity is generated, and the electricity is passed through this connecting wire. And if we have some device here, we can work, or if we can turn on the light, or we can use our some other devices. So here we are having that electricity is generated by the chemical reaction. So how it can happen, let us consider. This is an electrode, zinc electrode, and this zinc electrode, it is donating some, this copper electrode. First let us see in our here you can see, if where is our zinc, this is our zinc, and the copper is here. So zinc can donate electron faster than copper, is it? As we have mentioned in the reactivity series. So we have zinc, that means zinc in the above and copper in the below. So if we have a solution like this, zinc sulfate, here we have the zinc 2+, zinc 2+, here we have the copper 2+, and this is copper metal, this is zinc metal. So zinc 2+, this zinc 2+ is giving 2 electron to the solution to form 2. So zinc, what happened? Something here wrong. It should be minus. These 2 electrons should be here. Either it should be minus, or here it should be the plus 2 electron. 2 electron. So this zinc 2+ zinc metal, this zinc metal can donate 2 electron faster, and then it forms zinc 2+. So this zinc rod is decomposing to form zinc 2+ ion, and this 2 electron is accepted by this copper 2+. So this copper, actually this is copper sulfate, it is in aqueous solution, it becomes as copper 2+. Then as the electrons are transferred through this copper metal, that means copper metal, and then this copper 2 plus. This copper 2 plus is accepting this 2 electron, and then the size of the copper metal is increasing. So here you will see that this zinc rod or the zinc electrode will decompose, and after certain period of time, when we are using the dry cell or some battery, then the zinc rod or the zinc electrode will be decomposed and it will not be suitable for use. So here we can see that zinc is donating 2 electron to decompose to make the zinc 2 plus ion, and the electron is transferring through this, and this copper 2 plus is accepting this 2 electron. So here the reaction proceeds like this way, and we can represent, this is a half cell, this is another half cell, so this is a complete cell or full cell. So we can represent the electrochemical cell like this way. What is the representation? First the metal, and then the electrode and electrolyte, and then electrolyte, electrode. We will see the rule in next slide. So what is the rule, how we can write down the cell diagram, how we can represent or expressing a cell, the anode oxidation placed at the left. So previously we have seen that is the anode, the oxidation. This is our oxidation part, this is our reduction part. So oxidation part should be in the left side and reduction part should be on the right side. And then the cathode reduction placed at the right, boundary between different phases represented by single vertical line. So here we also can use this. This is one, this is in left side, this is right side. So boundary between different phases by single vertical line, we can use here one vertical line, here another vertical line, boundary between different phases represented by, so zinc solid and zinc aqueous. This is electrode and this is aqueous solution. So we are using one vertical line here. So this is H plus and this is H2 gas. So different phases for this one and this one different phase, this one and this one different phase. Then the states are mentioned if gas pressure is mentioned. So if we have all the states, we need to mention solid, aqueous, or if we have some gas or liquid, whatever the state we need to mention. And then boundary between half cell compartment. This is one half cell, this is another half cell. So the boundary between half cell compartment, commonly a solve, is represented by a double vertical lines. Here you can see double vertical lines. So by using this, we can have the boundary between half cells. This is one half cell, this is another half cell. So we are having two vertical lines. So here also previously we have shown, this is one half cell, this is another half cell. This is oxidation part, the anode part, the oxidation part in the left side. This is reduction part in the right side, and this is the separation between two different phases. This is one phase, this is another phase, solid, aqueous. So one vertical line, and between two half cells, this is half cell, this is another half cell, separation between two half cells, we are using double vertical lines. So a standard electrode potential. So what is this? A standard electron potential, that means when one metal donate some electron, it has the tendency, and when another non-metal accepts some electron, it has some tendency to accept the electrons. So just previously we have shown the reactivity series of metals. Actually, if we consider this is a very good metal, potassium, it can donate the electron very fast. So it cannot accept electron very fast. That means if it has the possibility, if it has the ability to donate electron very fast, then it has the least ability to accept electron. So we can consider the reduction potential for potassium would be the minimum. So if we consider like this way, the oxidation potential for this one would be the maximum and reduction potential for potassium would be minimum. So you can see here lithium, we are not having here potassium. So just in case of lithium, magnesium, so the reduction standard electron potential, this is minus. So it has the reduction potential for fluorine as maximum. So lead, chlorine, oxygen, all of these has those who has the higher position in the reduction potential. That means this series, this one will be able to accept the electron faster than any other. So if we have two different metals, copper and iron 3, copper 2 plus, iron 3 plus, then the iron 3 plus will have the tendency to gain electron faster compared to copper 2 plus. So that is the standard electron potential for any metal or any element or any substance. It has a certain value or tendency to accept the electron, and we can organize for hydrogen. Actually, the tendency of hydrogen is 0 to accept or donate electron. So we are keeping that the reduction potential for hydrogen or oxidation potential of hydrogen is 0. So above this, the very high reduction potential, above this high oxidation potential. Okay, so comparing with the value of tendency of gaining electron or donating electron with the hydrogen, we are having some value for the tendency of accepting electron of other metals, and we are giving this value for that types of elements, and that value are the standard electron potential for all the elements what we are having. This cell diagram represented a standard cell potential. So if we have a cell prepared from two different metals, let us consider copper and hydrogen. If we have the standard electron potential for copper is, we are reduction potential, we are having reduction potential for copper is 0.34 and reduction potential for hydrogen is 0. So if we make a cell out of copper and hydrogen electrode or copper and hydrogen system, in that case the total electrode potential for the copper and hydrogen, this cell, this is half cell, this is another half cell. So we will have the total reduction potential for this one would be 0.34. And if we make another cell made of either silver, let us consider the silver and zinc. If we can make a cell made of this zinc and silver, and if we put this zinc in the oxidation part and silver in the reduction part, then we can have the reduction potential, that means the full cell potential, that means the reduction potential of this 0.80 and the oxidation potential for zinc then minus 0.76. So that would be in the positive, because we have mentioned oxidation, this is the reduction potential and this is the oxidation potential if we consider. So in that case the 0.76 and 0.780 we will have to sum up. If we put this silver in the reduction half cell and zinc in the oxidation half cell, in that case we will have the total cell potential equal 0.76 plus 0.80. So here you can see, if potential difference or voltage of a cell formed from two standard electrodes, E0 cell, E0 cathode minus E0 anode, so H0 plus 2 electron. So if we have these types of system, if we have the cell part, if you have any question. What is the time right now? 7. Just I think I will not take more 10 minutes, maybe that would be enough. So just after 10 minutes we can conclude and you can go for the dinner, and that would be end for today. So if we have a cell, that means we have made a cell out of 2 half cells. Then we will have the cell potential, just E naught cell, we will consider E naught cell equal E naught cathode minus E naught anode. That means the cell potential of the cathode minus the E naught potential, that means anode reduction potential at cathode minus reduction potential at anode. So if we have a cell made of 2 different electrode and electrolyte, then we will have a cell potential E naught cell and E naught anode and E naught cathode, whatever, S plus 2 electrons. So I'm not going to show you all of them. Just you have to have these types of information, that if you have a cell made of 2 different types of electrode and electrolytes, then you have to find out E naught cell equal, that means this is the full cell potential, equal E naught cathode minus E naught anode. That means the reduction potential of cathode minus reduction potential at anode. So as we have mentioned previously, if we use 2 cell like this, 2 electrodes, silver and zinc, in that case we had the value 0.80 and minus 0.76. So you can have minus 0.80 minus 0.76. So that will give you the value what we are expecting. And battery is a device that stores chemical energy for later release as electricity. Already have mentioned. That means, so primary cell, the cell reaction is not reversible. That means that types of cell can be used only one time. That means the dry cell, what we are normally using in Bangladesh, you can have some Olympic battery or sunlight battery, these types of battery or these types of cell, this can be used only one time. So you cannot use, or it is not rechargeable. So that is primary cell. And secondary cell, the reaction can be reversed by passing electricity through the cell, have a lifetime multiple cycles. That means for mobile phone, we are using, after a certain period of time of use, the phone battery is completely recharged. Then when we recharge it, again we can get the system, that means system running. So what happens? The reaction can be reversed. Already I have mentioned in battery some chemicals are there. So when these chemicals react, they produce some electricity that is used to run some device, and that is normally for the primary cell. But in case of secondary cell, we have certain type of chemical that when we are using, that time it is forming, it is reacting to form the electricity, and when again we are passing some electricity through the chemicals, then some reaction proceeds and the chemical restore again. When this chemical reacts, they can generate some electricity. These are the properties of different types of materials or different types of substances, and so that are secondary cell, and the lifetime have a lifetime multiple cycles. We can use multiple times because we are, I'm using this phone for more than 4 years. So you can consider how much time we can charge and discharge it. So multiple cycles. Flow batteries and fuel cells. So materials pass through the battery. A converter of a cycle energy to electric energy can run indefinitely as long as electrolytes are supplied. So primary cell, in case of primary cell, as long as electrolyte it can have, or electrode. So as I have mentioned in one of the previous example, here you can see, if we consider for these types of cell, when this zinc electrode is no more, as I have mentioned that this zinc electrode is decomposing with time, and it is when one atom of zinc is releasing 2 electrons, it is decomposing as zinc 2 plus, and the electron, 2 electrons are passing through this. So every time 2 electrons pass through here, one zinc atom is dissolving into the solution. So the electrode is decomposing, or the size of the electrode is decreasing day by day or with time. So the electrode will be decomposed, and at a certain period of time or after a certain period of time, the zinc electrode will be decomposed and there will be no zinc electrode and no electricity will be produced, because no zinc electrode can be decomposed into zinc 2+ ion. So that time the cell is completely dead. But if we have some mechanism that we can regenerate the electrode, that can help us to reuse the system. That is happening in our mobile phone, but that zinc cannot be used. So the Lackland cell, what we have mentioned, that means that is zinc 2+. Here you can see anode half reaction. That outside we have a zinc coating, which is used as the electrode, and this is our graphite, that is used as cathode half reaction, manganese oxide and manganese oxide ammonium. Here inside we have some electrolyte, cathode half reaction, manganese oxide ammonium ammonium. And so this zinc electrode, when it decomposes, what we have shown in the previous slide, as I have mentioned, this zinc electrode is decomposing to form zinc 2+ ion, and it is giving some electrons, and that happens, this types of reaction happens in the Lackland cell, and that is the structure for the Lackland cell. And we are using, here we have some chemicals. This is kind of paste, you can consider paste of manganese dioxide. Actually this is a dry cell, what we have mentioned, that means Olympic or sunlight, whatever the dry cell we have in Bangladesh. So dry cell, normally in cell, previously we have what I have mentioned here. This is the electrolyte is in aqueous phase or solution state. So if you want to transfer these types of cell from one place to another, if you want to use continuously, that can be very difficult to transport. So that people have thought some idea that how we can change these types of electrolyte from liquid to solid. Actually this is the developed model of the cell, what I have mentioned previously for the zinc and zinc sulfate, and these are different types of material we are using. Zinc, this is zinc, it is forming, and then manganese dioxide, and then manganese dioxide ammonium. Here you can see paste of manganese dioxide, zinc chloride, ammonium chloride, and graphite carbon. So including all of them, if we make the cathode, then we can have the reaction like this way: the manganese dioxide plus 2NH4 plus 2 electron, then it is forming manganese oxide, and then ammonia gas and water. Actually we have some hole here, porous paper here, and some air space. So in this between these two, here we have some cap, porous paper, and then asphalt seal. Here you can see this is some seal, so that no matter from the inside can go outside. Even outside we have some metal shield, and then paper shield, and then we have some plastic covering. And normally the plastic is no use, but the plastic is used to mention different the name of the producer and the cost and the direction of the electricity flow and many other things, and how is the voltage of the this cell, how much electricity or how much potential difference it can generate. Normally the Lackland cell has the potential difference as 1.5 volt. So we are not going to learn this one. Actually the lead acid battery, that is used in the car. Normally in the car we use these types of battery. So we have many electrodes dipped into the electrolyte. So we can have huge amount of electricity. That means normally 12 volt or 24 volt. That can be, that means normally in the Lackland cell, what I have shown previously, Lackland cell give only 1.5 volt. But when we have the lead acid battery, these types of maybe 6, not 6, 1.5. Normally 8 or 12 or 14, 16 number of cells are connected in a series or parallel. By that way, we can have a lot of electricity, or we can generate high voltage between the cells. So we can have a huge electricity or the potential difference. So the combination of or the summation of many cells. Lithium ion battery, actually what we are using mainly in our mobile phones, that is the lithium ion battery. Actually you can see a lithium ion battery or lithium ion battery is a type of rechargeable battery composed of cells in which lithium ions move from the negative electrode through an electrolyte to the positive electrode during discharge and back when charging. So as I have mentioned in previous slide that here the electrode is decomposing. So if we have any mechanism that we can regenerate the electrode so that we can have the reaction again and we can generate electricity. So actually in the lithium ion battery we are having same thing. So the lithium ion battery is a type of rechargeable battery composed of the cells in which lithium ions move from the negative electrode through an electrolyte to the positive electrode during discharge and back when charging. That means when we charge this, we are generating the electrode. Lithium ion cells use an intercalated lithium compound as the material at the positive electrode and typically graphite at the negative electrode. So lithium ion batteries have a high energy density, no memory effect, and low self discharge. Actually, it do not use any voltage. So just low self discharge. Cells can manufacture to prioritize other energy or power density. They can, however, be a safety hazard since they contain flammable electrolytes. That is the issue when we mention that when we are charging, we should not use our mobile phone, because here you can see some safety hazard. So if we use the mobile phone while we are charging, what happens? Anyone can have an idea what it can happen? When we are charging our phone, that time the electricity is passing through the electrolyte so that it produce some chemicals. That means electricity is passing through the chemicals, and when we use the phone, if we do the same thing together, that means when we are using, the chemical reaction proceeds to produce the electricity which is used to run the device. So now if we proceed or if we do same time together, that means we are charging and discharging. That means the mobile phone battery both at the same time it is charging and discharging. That means both types of chemical reactions are happening. So the hazard, since they contain flammable electrolytes, and if it is damaged or incorrectly charged, can lead to explosion and fires. So it can have these types of problem. So when we are charging our phone, we should not use this one, because at the same time, if we are charging and discharging, that can be dangerous and it can be explosive, because some flammable electrolyte we are using inside the cell and in the lithium ion battery. And solar cell, we don't need electrolysis. Electrolysis, what I already have mentioned, you are using different types of spoons. This is the last slide. So electrolysis is the process by which we can have some chemical reaction by passing some electricity through the cell. Here you can see this is as electrolyte. This is an electrolyte. This is an electrode. This is another electrode, and this is some source of electricity. This is battery, or we can pass electricity. That means direct electric current. So when we are passing the electricity through this is the source. Actually, this is the positive pole and this is the negative pole of the electric power or the battery. So when electricity is passing through this, so like this way, so the copper plus, so electron is passing like this way, so like this way and continuously it is happening. So when electricity is passed through this electrolyte, this copper plus, that means copper plus ion, it is gaining the electron because electron is coming here. So you can consider that copper in the electrolyte, you have the copper plus ion. This copper plus ion can gain the electron, so it will have copper plus electron, it will become copper metal. So in that case you can have the idea that this copper, this cathode, the size of the cathode will increase while the electricity is passing through the electrolyte, the copper plus or the electrolyte ion will gain, or it will gain the electron and the size of the electrode will be increased. So we can have more copper in the electrode. Now you are using different spoons. Most of the time the spoons are made of iron and you can see some silver coating over that. So what we are doing there, we are having some silver electrolyte and this is our iron spoon. If we use this the iron spoon, so we can use the iron spoon as the electrode, and electrolyte we are using the silver ion. So when this silver ion, that means electricity is passing through this, so the electron, that means silver ion is gaining electron from here, that means this is our metal, that means iron spoon. So this iron spoon is gaining silver ion over this, because we have mentioned that the silver ion is here and silver ion is gaining electron and silver metal is deposited on the iron spoon, so that we can have that iron metal is coated with silver metal. Therefore the spoon what we see like a silvery, that is the coating of silver. Inside everything is metal. Most of the time, not only this, some wristwatch and many other things we are using, all of them have the inside is iron and outside some coating, sometimes the golden coating or some other coating. So we are using different electrolyte over the iron metal to make a coating. So we are having these types of process that is known as electrolysis. The reaction proceeds by the passing of electricity, that is known as electrolysis. So this is the end of today's class, and if you have any question or comment regarding this, then you are welcome. Yeah, class is over. So just I want to stop the recording.